Okay. Should I start? Or?
Yeah, maybe we can start. So, hello everyone. Today we will discuss a paper on recommender systems. And this paper has a special focus on debiasing the popularity in recommender systems. The main reason is because the recommender system we have so many popular items and popular users, which may create some biases. For the recommendation results. In this paper, the model will be try to do the debiasing of the recommender system in terms of the popularity. And the presenter today will be Chongzhou Fang, right? And so we can give the time to the presenter. And Chongzhou, you can start when you're ready.
Okay. Hi, everyone. My name is Chongzhou Fang. I'm a second-year PhD from Department of Electrical and Computer Engineering. So today I'm going to present this paper, Model-Agnostic Counterfactual Reasoning for Eliminating Popularity Bias in Recommender Systems. So as indicated by the name, this paper is focusing on recommender systems. And the problem is trying to solve is to eliminate the popularity bias in recommendation problems. So I will cover some basic backgrounds of recommender systems, and I will introduce some concepts that is utilizing their research, and I will present the method, and finally I will present the results and show that why this method is superior compared to other debiasing methods. So recommender system is widely used nowadays. Recommender systems is basically a tool that provides personalized suggestions to users. It is trained based on past interactions with user item interactions, and may generate items that a certain user might be interested in. So one example is shown in this funny comics. So it indicates that customers who buy banana may also buy some other items. So that's how recommender system works. It infers some of your preferences based on your past interactions with items. So recommender system is actually widely used in nowadays content distribution platforms. For example, if you go to YouTube and it will recommend you some videos, and these videos are based on your past watching history. If you go shopping, Amazon will also provide you the list of products you might be interested in. And even when you try to listen to some music, or when you want to play games, those platforms will use recommender systems to provide you with some items you might be interested in, so that it increases the chance of the chance for you to interact with these items, and therefore increase their profits. Besides the usage in content distribution platforms, actually recommender system can also be used in other fields. For example, my research area is data center scheduling or cloud scheduling, and there were two papers 10 years ago that was cited a lot that utilized recommender system to optimize for scheduling algorithms. So in these papers, they consider each item as a user, and the configuration for the item in the data center as each instance as user, and the configuration as items in a traditional recommendation problem. And the method they use to recommend is collaborative filtering, and they can use collaborative filtering to recommend configurations for instances in the cluster. Therefore, they can increase the quality of scheduling. So we can see that recommender systems are quite widely used, not only and they are used in different fields. However, there is one problem that has not yet been very well solved. It is called the popularity bias. So popularity bias is the cause of popularity bias is very simple. So because the recommender system is usually trained on a training set that consists of past user interaction data, and of course the interactions are biased towards those popular items. So as a result, the generated the outcome of the recommender system will therefore be biased towards popular items. This will reduce the accuracy of the recommender system. So the figure in this page is one example from the paper, and from the blue bars. The blue bars are the frequencies of the items in the system, and we can see that for items that appears not very often, the recommendation frequency is very low. But for most popular items, we can see here, for most popular items, the recommendation frequency becomes very high. So this can sometimes be annoying because I shouldn't say annoying. This does sometimes be suboptimal because users may not always be interested in popular items. For example, you use Netflix and you have some very special taste, but Netflix keeps recommending you popular items and which you are not interested in, and that will result in a useless recommendation results. So in this paper, the authors tries to propose a model-agnostic method to solve this problem, and by integrating several modules to the original recommender system, popularity bias can be eliminated by a lot. We will see the results later. So before we dig into more details of their work, we will first take a look at the problem definition. So in a typical classic recommender system, there are users where there is usually a user set, U1, U2 to UN, where N is the number of users. And also there will be an item set, I1, I2 to IM, where M is the number of items in the item set. So this can be understood so for example, you are an engineer in Netflix, and you will represent the set of users in your platform, and I is the set of movies on your platform. So besides you and I, there is also another variable called user item interaction, Y. Here, Y is a matrix, and it's an n by m matrix, and the entries are defined as YUI equals 1 if user U has interacted with item I, and 0 if user U has not interacted with item I. So basically, this matrix records the past interaction, records the interactions of users, and may contain information of whether a user is interested in certain types of items. So the goal of a recommender system is to learn a scoring function from the user item interaction Y. This function F is the function of user and item embeddings, and it will generate a score which represents the preference of a user U over item I. So that's the basic problem setting of a recommender system. And in this paper, the users are trying to study how to eliminate a popularity bias. Therefore, traditional evaluation methods that do not consider this bias cannot work well. So in this paper, we will see later in the evaluation section, they use a debiased evaluation method, which samples the data set and generates a generates a test set that is a uniform distribution of sampled items. So concludes the problem setting. Now we can get into some more details of the technology. So first of all, I'm going to introduce some basic concepts. The first concept here is causal graph. A causal graph is defined as a direct acyclic graph. G equals to VE, where V nodes in the graph are the set of variable, and E is the edge set is the cause effect relations among variables in V. So for example, you have node A and node B in your system, and there is a connection between A and B. It means that A is the cause of B. So some notations that will be used later, I will just show here. So capital letters typically means variables. For example, if you see a capital letter I, we mean the variable I. But for the observed values of I, we use lower letters. Yeah, so that's the difference in the notations of variables and observed values. So an example of causal graph is shown in this slide. So here we have three nodes, I, K, and Y. And if we see Y as the target variable, then I is the input variable, and I can influence Y in two paths. The first path is directly from I to Y. Here, this path is defined as the direct path. And the second path is I to K, and from K to Y. This is defined as an indirect path. And to calculate the value of Y, we will, as shown in this figure, we will plug in the number, the value of I and the value of K to the scoring function to get the value of Y. And here, the observed value of K is calculated by plugging into the observed value of I to the scoring function of K. Here, Y, K are both value function or scoring functions. In practice, scoring function, these value functions can be replaced as neural operators, for example, fully connected layers. And these layers will perform the task of calculating values for nodes K and Y. And in this graph, the prediction direction is from I to Y. And to do this prediction, it has to consider both the direct effect from I to Y and the indirect effect of I to K to Y. So this is the concept of causal graph. It basically defines a set of nodes and the relationships and the causal relationships of these nodes, and we can infer the causal relationships from this causal graph. Causal effect is one concept derived from causal graph, and it's defined as the causal effect of I on Y is defined as the magnitude by which the target variable Y is changed by a unit change in an ancestor variable Y. So to have a simpler explanation, it means that it measures how much it measures the change in Y when I change when the change in Y with the change in I. So to calculate this causal effect quantitatively, the authors defined several equations, and they defined several variables to measure this causal effect. The first one is called total effect. It's calculated by directly subtracting yi, ki, and yi star, k star. Here, YIKI is represented by this graph. It represents the state where I equals to I. And here, this one is another state of the system where the input I equals to I star, and the intermediate variable observed variable k equals to k star, and the outcome y is denoted by yi star and ki star. So basically, this total effect measures the difference between two situations, I equals to I and I equals to ki. And usually, I equals to ki is a counterfactual situation. We usually use, later in this paper, we will set I star as the main of I in the training set, so that it can be a reference point, it can be a reference point. So this is the concept of total effect. And starting from the total effect, the author defines two separate components of total effects. One is called natural direct effect. It is defined as yi ki star minus yi star ki star. So here, yi ki star is calculated by directly plugging into I equals to I and k equals and I equals to I star to calculate k. So the calculation can be understood in an easier way if you take a look at this picture. So yi ki star is this part, and different from previous nodes in the previous figures. It is partly counterfactual, which means the direct path is factual, but the indirect path is counterfactual because it involves counterfactual values. So we can see that this natural direct effect measures the direct effect through I to Y. So I can see that it takes into ki star as the one input and does this calculation to eliminate this path so that it gets the direct effect of this path. So the counterfactual values here is ki and also the calculated result yi star. So this is the concept of natural direct effect. The takeaway knowledge here is that it measures the direct effect from one variable to the other. So derived from that, we have another concept called total indirect effect. The calculation is basically just using total effect to subtract natural direct effect, and it will result in this equation yi-ki minus yi-ki star. So it basically measures the effect of this path. It measures the effect of I on Y through the indirect path I to K to Y. So this concludes the introduction to the concept of causal effects. So in summary, total effect measures the change caused by the change of value I, and natural direct effect measures the change brought by this direct path, and total indirect effect measures the change brought by this indirect path. These are very important concepts, and it will be utilized in later methodology section. So by using the previously mentioned causal graph, a recommendation system can be modeled as shown in the figure in this slide. Here, the causal graph has several components. The first one is node U, which means which represents user embeddings. item node I, which represents item embeddings. And here K is the user item matching features. And finally, Y is the ranking score. We can consider Y here as the target variable. And here both I and U will influence Y by this indirect path. Here, it's worth noting that the matching function here, KUI, learns the matching features between user and item, and this scoring function, YK, will assign scores and finally become the output of this recommender system. So this is a very classic causal graph representation of a recommender system, and so there are some example recommender systems in the literature utilizing this model. For example, the one called MF, the one called NCF. They are mentioned in the two papers listed here. So the problem of this model here is that we can see that I and U can only affect Y by this indirect path. And some important connections are discarded. For example, user conformity, which means the inference brought by user, and item popularity, which is the inference brought by item features. They are both ignored in this model. So to solve this problem, we may add path to this figure, and incorporate some other variables to predict Y. For example, by incorporating path I to Y, we include item popularity into the system. By adding the path U to Y, we incorporate user conformity to the system. And there are already examples of recommender systems utilizing this model. The MF with traditional terms of users, and a new MF, both utilize this model. They related references are in this slide. So let's compare these two different models. So in the first model, the target variable Y is only the function of KUI, which means it when during the process of scoring, it only considers user item matching. While in the newer model, Y is the function of U, I, and KUI, which means that it not only takes into user item matching K into consideration, but it also takes into user conformity and item popularity into consideration. But the problem here is that existing work, they simply just add certain entries into the scoring function, and during training, both these two models are treated equally, which means that they have the same loss function, and they only follow the same backpropagation path. So usually to train this network, they use BCE loss, which is defined in this equation. It is a very typical cross-sample entropy loss. D here is the training set, and this sigmoid, this is the sigmoid function, and the YUI here means either YKUI or YUI KUI, because in previous literatures they treat these two models equally in both training and testing. So this is not ideal because popularity bias problem still occurs, because YUI is inferred from the training set, and the training set is highly biased towards popular items in the data. Therefore, as a result, the the trained recommender system will be biased towards popular items, which means it will recommend popular items more often than you want. And the problem here, the cause of the problem here is that this path of inference I to Y means the popularity, the item popularity can in fact affect the outcome of the recommender system. Therefore, the inference of this path needs to be blocked. So that's where the intuition of this work comes from. Basically, it will introduce an additional item to cancel the effect of this path. So let's now take a look at their methodology. So their proposed framework is shown in this slide. Besides the classic recommender, the authors also introduced user module and item modules. So user module considers the path from user to Y, which is the output of the recommender system. And it is calculated by a value function YU by plugging into U equals to user embedding U. And this user module measures to what extent the user would interact with an item, even when preference of this item is not matched. Basically, it takes into the effect of user features. So an example here is that it's shown here. So, for example, user A has a broader preferences, and therefore it clicks more videos than user B. And in our system, user A can be considered an easy user, and therefore will be associated with a higher value of user score. And this easy user A will be more prone to be affected by item popularity. So by integrating this user module, we are able to consider the effect brought by user features. Second path it is considered in this framework is the path from I to Y, which is this one is called item module, and same as before, it is calculated by integrating a value function. And this path reflects the influence of item popularity. So usually more popular items will obtain higher YI. So by integrating this item module, we are able to model item popularity. So finally, the recommender here, the recommender works in the same way as in traditional recommender systems. It takes into user item interactions, and it generates some matching results, and then finally it is calculated by a value function YK. So it's basically the ranking score from existing recommenders. So from this framework, we can see that the authors call this model a model-agnostic model, because the recommender here can be arbitrarily replaced as long as user module and item modules are able to be integrated. The users can construct a newer model that can eliminate the effect brought by item popularity. So next question. So how are predictions aggregated? So here to generate the prediction result YI here, we use this equation YK times sigmoid YI times sigmoid YU. So this is a sigmoid function to scale YU and YI to 0 to 1, and it adjusts the extent of reliance upon YK. So for example, to recover the interactions between inactive user and unpopular items, the model will be pushed to highlight user item matching YK, which means it will enlarge the value of YK. So So the next question is how this framework is trained. So the authors introduced several training losses. The first one is the total training loss, which is calculated by training loss of LO, which is the loss function we showed before. It's the loss of cross-entropy loss of recommender system, plus alpha, which is an hyperparameter, times the loss from item module, plus beta, which is another hyperparameter, times the loss from user module. So to calculate the recommendation results, the authors propose a counterfactual interface, which will help remove the popularity bias. The basic idea here is to block the path between I and Y. So they propose a new method to perform recommendation. So instead of directly using the score generated by original recommender, it introduces another item to adjust this value. And here we can see that C is the hyperparameter, another hyperparameter, and sigma, and here sigma yn and sigma yu also both sigma yn and sigma yu incorporates the effect from item popularity and user conformity. And by doing this abstraction, the authors are able to cancel the effect of item popularity. So I will show how this actually works later in later slides. So one example of this recommendation system is shown in this slide. So for example, we have two items, and item J is much more popular than I. So according to the algorithms of original recommender system, item J will be ranked in front of I because it's more popular, and because the recommender system is biased towards popular items, it will generate a higher score for item J. However, by introducing this item, we are able to cancel this effect because now we take popularity into consideration, and because item J is more popular than I, so it will obtain higher score in this item, which will result in a larger value being subtracted from the original score. Therefore, the final result may be that item I is ranked in front of J.
I have a question in the previous slide.
So,
is this C constant here? I mean, like there are
yes,
situations where you would want.
Yeah, it's a hyperparameter.
There are situations where you would not want to subtract this part. I mean, like there are situations where certain items are popular and there is high user conformity, and you would want the system to recommend popular items. This it seems like this equation will not allow popular items to be recommended if C is a constant. I mean, like I don't quite understand the purpose if C is a constant for every item and for every user, independent of the conformity or item popularity.
Okay, actually C has its exact definition. I will show that later. It's actually the value of the result of the value function K by plugging into counterfactual inputs U star and Y star. I'll show that later in another equation. So yeah, you are correct. When there are higher user conformity, and when the item is very popular, I think it can indeed result in popular items not being ranked very high. Yeah, I think that's a very valid. That question is a very good question, and I think the authors didn't actually consider this, and they just proposed how to block the effect of this pass.
All right, yeah, thanks.
Okay. So now I'm going to introduce the biased interface in more details. So here, can see that in this model, Y is affected by two paths, I from K to Y and I to Y, and also U to Y. But because we only consider item popularity, so we don't take it into consideration. And here we will introduce a counterfactual interface, so therefore we can calculate the causal effects of item popularity and then block them from the recommender system. So that's how we do it. So first of all, we introduce a counterfactual phase where we plug into counterfactual values U star and I star. Here, U star and I star are usually set as the main values of variables, and here it generates a counterfactual K value, and then we will consider the natural direct effect. So according to the equation we shown in slides long before, natural direct effect is calculated by this. We plug into factual values of U and I and counterfactual value of K, and use it to subtract counterfactual values, counterfactual score. So you may recall, this natural direct effect measures the influence of this path. Then the total effect is calculated here. Total effect is calculated by plugging into U equals to U, I equals to I, K, and K equals to KUI, which is a factual set of variables, a factual set of values, and also they also use this to subtract a counterfactual a Y score Y calculated by all counterfactual values. So as we mentioned before, total effects consist of the direct effect from I to Y, as well as the indirect effect from I to K to Y. So to eliminate popularity bias, instead of using total effect, the authors propose to use total indirect effect, which is calculated by TE minus NDE, and it will result in this equation. So recall that we already have our score function U equals to U, I equals to I, and K equals to UI. So to calculate, therefore we are able to obtain this item. To calculate this this counterfactual item, which models to calculate this counterfactual value, what you need to do is to basically plug into factual user embeddings, factual item embeddings, and a counterfactual value of KUI. So we are supposed to get a value here times sigma yi times sigma ui, and here this value here C is actually yk with k calculated by a counterfactual value. So I think this answered the question that was asked just now. C here is a hyperparameter, and it is defined by k equals to KUI, and yeah, and then we used this item. We used the calculated original score to minus this item. So therefore, we are able to block this in this direct effect. The key takeaway knowledge here is that instead of using total effect of variables, the authors propose to use total indirect effect, which does not contain the inference brought by item popularity. And they use this total indirect effect to perform recommendation. So that concludes the methodology section. Now it comes to the evaluation. So first of all, their experiment settings. In this paper, they evaluate their MACR method based on several different data sets, which includes ML10M, Adressa, Global, Gowalla, Yelp, which are all data sets that is frequently used to evaluate recommender system. It's worth noting that in these data sets, items are actually very biased based on popularity. So to evaluate this convention, because this paper targets to eliminate popularity bias, and if we use conventional evaluation, we are not able to obtain the result of our method, because the conventional evaluation does not take into long tail distribution. So in this work, to simulate the bias recommendation, they also sample the data set and create a data set that's uniformly distributed over items, and use that to test the recommendation quality. The metrics here, metrics used in this paper are hit ratio, which is the ratio of matched recommended items. The recall score, which is defined as the size of hit set divided the size of test set, and the normalized discounted cumulative gain, which is another widely used measure to evaluate ranking quality. So in this evaluation section, the authors tries to answer 4 research questions. The first question 1, does MACR outperform existing debiasing methods? Question 2, how do different hyperparameter settings, alpha, beta, and C, affect the recommendation performance? And question 3, how do different components in our framework contribute to the performance? Question 4, how does MACR actually eliminate the popularity items? I will show their answers to the 4 research questions one by one. The first research question, does MACR outperform existing debiasing methods? They also did some evaluation based on several data sets, and they use MF and light GCN as background background recommender, and then they incorporate different debiasing methods to these 2 recommenders. And as shown in this result, MACR outperforms in every matrix, in every data set. So the answer to the first question is yes, MACR outperforms existing biasing methods, and in every case, it even boosts the performance by a large margin. And there are some interesting findings from this result. The first one is that we can see that light GCN, which is one recommender in literature, usually performs a little bit worse than MF, which is another recommender in literature. And so in this figure, we can see that light GCN always recommends more popular items than MF. So these two observations combined means that light GCN are vulnerable to popularity bias. However, by integrating our MACR method, light GCN now actually performs better than MACR MF. So this means that our MACR method actually works, and it helps light GCN eliminate the influence of popularity bias. The second interesting finding is the results on global. So global is a news recommendation set, and this kind of data sets are usually quite biased because popular news are read very often, but not those news that are not popular may be clicked only a few times. So we can see from the results on global that our methods can actually improve on this long tail data set. So we have answered the question 1, and now we target question 2. So question 2 is basically an ablation study, and question 2 basically studies the effects of different hyperparameters. So to evaluate the effect of different parameters, the authors fix the other parameters and only change the current parameters to, and they provide screening results on the recommender system. So the first one, the authors explore the effects brought by different choices of hyperparametricity, and we can see that in both figures there is a best choice of C. So take this large GCN as an example. Before reaching 29, by increasing C actually helps improve the performance. But after reaching this optimal point, further increasing C will result in worsened performance. So these two figures show that actually there is an optimal choice of this hyperparameter C, and the designers of the recommender system should pay attention to this choice. And also from these two figures, we can see that light GCN actually, the performance of light GCN actually drops more sharply compared to MACR MF, which again shows that light GCN is more sensitive to this choice of parameter C. So it comes to parameter A, alpha and beta. As you may recall, these are two parameters used in the loss function. So the authors provides different values of provides the system with different values of alpha, and then it tests the performance of the MACR recommender. And as showing this slide, actually there is a best choice of alpha as well. You can see that before reaching 1E-3, the performance increases, but after reaching this point, further increasing alpha will result in a drop in performance. The situation is the same for hyperparameter beta. Still, there is a best choice for beta. And it's worth noting that as this alpha and beta controls the proportion of user item, the proportion of user conformity loss and item popularity loss in the training loss. So if alpha and beta becomes too large, the training of recommendation model becomes less important. And we should know that why the recommender system works is because there is a recommender integrating the system. And if we increase alpha, if alpha and beta becomes too large, the training of recommendation system becomes less important, and it will lead to worse performance. So then it comes to research question 3. How does different components in our I saw the question in the chat. Isn't creating a new test set for the version almost cheating? Only this model has been designed to work well on this test set, and it's quite hard that any other model can outperform model that is designed for this evaluation set. I think that's a valid argument, but as we let me see. As we can see later, actually, if we test on the original data set, we can see that the popular items are actually the frequency of recommending popular items actually decreases. So I will show the corresponding results later. So let's come back to the answer to research question 3. Research question 3 is basically an ablation study, and it's the answer to this question requires comparing MSE-IMF with several different versions of it. The first version is MSE-IMF without user branch. The second version is it without item branch. The third version is MSE-IMF without without item popularity loss, and the final version is MSE-IMF without user conformity loss. Here, some people may be confused by the description here. So to clarify, when we say without branch, it means that the whole branch in the causal graph is removed. While when we say without loss function, we mean that we only block the effects during training, but the inference on prediction is retained. The results are shown in this table. We can see that the original MSE-IMF actually performs the best, and if we remove any branch or if we remove any loss function, it will result in worse performance. So this result means that every component in the MSER framework is important. Finally, the answer to the question: does MSER eliminate the popularity bias? So the authors present these two figures, and we can see that compared to light GCN, actually MSER light GCN does decrease the frequency of recommending popular items, and the improvement on MF is even higher. And besides frequency, we also compare the item recall. Item recall is the proportion of an item being accurately recommended to users. So we can see that after integrating MSER method, the recommender models actually works better than before because it now achieves higher recall scores. So that concludes the evaluation part. Finally, some related work about popularity bias in recommendation systems. So previously, item popularity has been noticed by the research community, and there were a few methods proposed. The first one is inverse propensity weighting, which means you reweight the interactions of user item direction. For example, you impose lower weights on popular items, which will result in different rankings. And the limitation here is that it ignores the inference of popularity at all. And we can see that in our previous method, we only blocked the probability by a certain amount, which is controlled by C, but we still consider the inference of popularity. The second method is ranking adjustment. One method in this direction is to bring regularization to improve rank of low tail items, and basically all methods in this research path is a trade-off between accuracy and coverage. And because it's a trade-off, it will definitely result in an accuracy drop. So here comes the conclusion. I think this paper is the first paper that considers cause effect to alleviate popularity bias. It proposes MACR, which is Model-Agnostic Counterfactual Reasoning, which utilizes counterfactual reasoning to infer the inference of item features. There are the few future work that is possible. The first one is to better capture user conformity and item popularity and further improve the performance of this method. And the second one is to incorporate site information and further debias of item popularity. And the third one is to consider other biases, because in this paper the author introduces a cause effect view for recommender systems, and it's possible that these methods can be also applied to other biases. So this is their last possible work. So thank you, everyone. That is my presentation for this paper. Now it's time for Q&A.
Okay, so the talk is very good. And any question from students? There should be some question. No question?
I have a question.
Yeah,
So
go ahead.
in the paper, they don't really mention like training times or it's like inference time. I mean, I might be wrong. It might be written like in the appendix, like the sort of added like papers or like section at the end, but I didn't specifically see any mention of like how long this adds in terms of like wall clock time on in like during inference tasks. So do you know anything about that?
I don't know anything about that actually, because I also didn't see any description of related information. I guess that's because the focus is on improving the performance of the recommender system. And I think from the algorithm, I don't think the inference time will increase by a lot, because it basically just adds another. It's basically just subtracts another an item from the original score, right? So the inference time wouldn't be extended by a lot.
I see. But what about training time? Because now you, instead of just having like user to item matching, you also have you know, popularity, and you have these two added sort of features that you have to sort of learn with the causal graph, if I understand correctly. Do you think like during training this would like affect the training time, because like now we have more things to sort of learn?
Yes, I think so, because because they also introduced several other two other loss functions, and that will of course increase the amount of computation that's required. So I guess the training time will be relatively longer. But
I see.
Yeah.
Do you think it's like a good trade-off, that like in terms of the like performance you get out of it? Do you think it's just the added training time is like justifiable? I think looking at like just the quality like column of the table, it feels like it was justified, because in like most cases, like the performance was like really improved a lot.
Yes, I think this is it's worth it because the inference time, as we discussed before, may not be increased a lot, and even if we consider the chaining time, it's just another two loss functions in integrated, and I don't think it will affect the chaining time by a lot. Yeah, so I guess it's worth doing that, worth introducing this texture modules.
Thank you.
Yeah, I have a follow-up for comments for this question. So, I mean, according to the method they propose in this paper, I mean, the encoder they use, they have two different encoders according to the experiments. The first one is called matrix factorization. The second one is GCN, right? If I'm correctly. Actually, the encoder, I mean, this part, they try to compress the recommender system into the user representation and item representation. Then the main difference compared with the conventional recommender system lies in how to define those functions. So given the encoder or embedding vector of user and items, then we can further define the inference result for the labels. And in this method proposed in this paper, they, I mean, define several more terms, I mean, for define those functions. And then they try to maintain the true bias and popularity factors in defining those functions. So I think that the time cost will be slightly higher than conventional recommender systems, but it will be probably be comparable, right? Because the main difference lies in how to define those functions, right? And the encoders will be the same generally with the conventional recommender systems.
I think from this figure, they seem to be parallelizable, right?
Yeah, so
can also
from
further
user item to the user model or the conventional recommender system, this part is for the encoder, right? Like GCN or the matrix factorization. Now, given the embedding vector that you can further like define the prediction labels, right? Either for the user model, you can just use like a multi-layer perception to generate the Y hat. Right? Similar for the central part, they can concatenate the user item vectors for generating the Y hat K as well. So this part is very, how to say, it's very trivial, right? Because the main time cost lies in how to define encoders, right? As to how to define those functions based on the inference labels, then this part probably is comparable. Of course, there will be more factors to be calculated. I think the time cost will be slightly higher, but it will be comparable to the conventional recommender systems because the time cost on encoder will be very similar, right? Yeah, I also see the question in the chat from Barry. So,
okay.
And
yeah.
maybe you can respond to the question as well.
Okay. Yeah. Would this also, if approach also remove the effect of the quality of the movie on the prediction? How can the model differentiate between quality with when calculating the score of item branch? To be honest, I don't have an idea on. I don't have an answer for this question because in this paper, the idea is to just remove popularity. So yeah, and the authors only evaluated the influence on popularity bias. So I guess they only consider item popularity. So I don't think they considered so deeply. That I don't think they considered quality vs popularity. Yeah. So you can see from the results that they just put this result and show that more popular items are recommended less frequently, and that shows that popularity bias is eliminated. You know, I hope that answers your question.
Okay, so yeah, any more questions from students?
Hi, Professor.
Yeah, sure.
Yeah, I have a question for you, but I mean
Oh,
on the
okay.
yeah, I mean in when we imply this kind of model, like say into the industry, and how do they update the parameters in the models? Because we know the recommendation system, it should update every day or every minute, every second. They'll be in the optimum condition. However, it is not practical in my understanding, because the model, they'll be trained on the new data set and then adjusted by everyone behaviors. But when we have millions level the customers or the users, and how could the model to adjust this very large volume data, and how do they update itself? That's why I ask you. I guess you have more experience in that.
Yes, this question actually depends on different components or different services, right? So this is a learning program. It's called online learning. Online learning means you can update the models according to new data coming, right? As we have new data coming, we can keep updating the models according to the new data. Actually, when we see the service deployed in the websites, they are doing the testing actually. You can see recommendation of some friends on Facebook. They are all the testing results by feeding your data into the model, and they can generate some testing results as a recommendation result for you, right? So this is for testing when we see the surveys from the websites. And at the back end, they also update and train the model. You don't see that, right? They use the data in the database system and they train new models all the time. As they have new data connected, then they will update the models with the online learning techniques. This online learning can minorly, also gradually update the models. But sometimes, at some time points, if we have some significant data changes, then we can do the retraining of the whole model from scratch again, according to some time ranges, right? It really depends on the company or the services. So they have some online learning techniques, to update the models. Sometimes they will also retrain the model from scratch again, depending on how much amount of data coming, in terms of new data, right? So it will be very different for different components, right?
Okay. Thank you, Professor. So this model is based on, say, static data set, not a dynamic one. So I'll say the more practical dynamic data set from the industry, right?
Yeah, this one is a static recommender system. They didn't consider temporal factors in terms of new data coming, right? It's kind of trend. As to a dynamic recommender system, it will be different, right? There will be new factors to be considered in the evolving trend for both views and items. It will be different, right?
Oh, okay. Sorry. It's just an open question. Is there any real-time, say, dynamic adjust self-learning, something like this model, recommendation model, or is there any related research on that?
If you search online, like online recommender system or online learning plus recommender system, you can see a bunch of papers. Right? It's an old topic. Recommender system itself is a very old topic, and we also have some separated conference focused on recommender system as well. And as to a temporal recommender system or dynamic recommender system, there are so many papers there. It's a very mature topic already. Right?
Oh, I see. Okay, yeah. Thank you, Professor.
Yeah, anytime. Also, I also have an open question for you, for Chongzhou, for the presenter. Even though in this paper they claim they are doing a debiasing in terms of popularity, however, from the website, the service provider perspective, in material time, we may, like for Amazon, we want to recommend the item for the users, right? The main objective is to maximize the revenue. We hope the user will click or buy the items, no matter if it's popular or not, right? And also in many times, the popular items, they can receive more transactions, right? More people will buy popular items. So is this necessary to debias the popularity for like Amazon or not? Because even though they claim that debiasing of popularity is very important in this paper, however, in the real world applications, do we really need to do the debiasing or not?
I guess some certain extent of debiasing is required, because if you only recommend very popular items to users, actually I don't think they will exactly match the user's interest. And I think that this, by introducing this certain type of debiasing, we are able to recommend products that better fits the user's need, and yeah, better fits the user needs. And in this case, the users will click on. Are more prone to click on those items and even purchase items. Otherwise, if we consider popularity, if popularity does have a very strong influence on the recommendation outcome, then I guess it doesn't match the user's interest very well, so that it will possibly harm the profits of the commercial platforms like Amazon.
Okay, but in reality, people like popular items, right? Like if you watch, I mean, according to this website in China, it's called iQIYI, or the Chinese version of Netflix. They don't have like a very serious recommender system at all. They just provide the most popular or most hot videos or movies at the front page, right? So according to the CTO of this kind of company, they say these popular movies, they receive more, click rates than the recommender system they build. So people like popular items, actually, they want to buy popular items in most of the time, right? So it's also an open question, for the service provider, do they really want to do the debiasing or not? Or they just want to maximize the revenue? If they only want to maximize the revenue, it would be a different story, right? They don't necessarily need to consider debiasing this kind of issue at all, right?
Professor, I think in real world, I think the company have to show to users both personalized item and then popular item, because according to long tail theory, even the user have unusual taste, they also buy popular item when they buy the unusual taste item. So I think in real world, for example, Amazon, they also have to show the popular item and the personalized item to users at the same time.
Yeah, that's true. Normally, they will recommend both popular items as well as something that they prefer. At the same time, among the items that user prefer or like, in many of the cases, we also like the popular ones, right? If we have different options, match our requirements, match our needs, we prefer to buy someone with higher, trading records or transaction records, right? Now, if I want to buy a cell phone, normally I buy an iPhone or buy some Samsung phone, right? So I don't know. It really depends on the scenario, right? For the services, yeah. But in a way, I think they try to propose a new direction for the debiasing in this paper for recommender systems. As to either it will be useful or not, it depends on the application settings. Yeah. Thanks so much, Ming Sheng, right? And for the points. Oh, okay. Anyway, any more questions from students?
Actually, I think that studying debiasing also has some other. Actually, it's meaningful because now I think when we go back to the example when I proposed at the very beginning about data center scheduling. Here, if for example, if you collect data where users use very popular virtual machine instances a lot, and your recommender system will actually recommend you with very popular instances, which may not be very optimal for the profits of these data centers. So they may have to do the biasing and then try to find the exact match of the instance type for the user and then do scheduling. So that is just one of my thoughts. And I think in this scenario, debiasing is worth studying.
I see. Yeah, so anyway, I think this paper they propose a new, it's a very good point, right? Because fairness or debiasing nowadays is very hard nowadays. In both computer vision, natural language processing, also now in recommender systems. In the next class, we still have another paper on the bias issues in recommender systems. And so Also a reminder for you, I mean, we only have about 2 weeks left for this course. I think it's time for you to start work on your final project and start to write your final paper with your teammates. And we only have about 2 weeks left, if I'm correct, right? Yeah, start work on them earlier, then you have more sufficient time to finish the paper before deadline. Yeah. Anyway, thanks so much for time and attention today. And the talk is very good. Thanks so much, Chongzhou. Right?
Thank you very much.
Okay. Oh, let's also sing a speaker. Yeah. Thanks.
Thank you very much.
Thank
Bye.
you.
Okay. So maybe that's it for today. Thanks for your time. Yeah.
Thank you. Bye.
Yeah. Bye bye.